Hi, this is Liam 1981. Thought I'd make a bit of a video about DC protection circuits for amplifiers. I'm currently working on an amplifier. I'm slowly building up, and one of the main things you want at the output is the ability to disconnect the speaker should a fault happen within the amplifier, causing an amount of DC to appear on the output rail. So I'm going to run through a few circuits, some of the advantages, some of the disadvantages. This here is very similar, if not practically identical, to the basic DC protector Rod Elliott has on his Elliott Sound Products webpage. If we look from the output and work our way backwards, so we have the loudspeaker, we have a relay, we have the transistors that drive the relay, we have the transistors which form the detector circuit, and then we have the diodes which stir the output depending on whether it's negative or positive to make sure it can still activate the detection transistor. And then we have a resistor capacitor filter circuit which basically attenuates AC coming from the amplifier but allows DC signals to pass to activate the detection circuit. Now the relay, we configure the relay so that the normally closed pole connects to 0V as well as obviously the speaker connecting to 0V. So if there is a fault, as the relay opens, if an arc is struck across the relay contact and it tries to be maintained, because obviously once an arc is struck it only needs a very low voltage to maintain it, it will short across to 0V rather than flowing through the relay. And even though the terminal's open, an arc could still jump across. If this was just left floating, or we just had a single pole relay, it could still flow across and the current would pass through the speaker. So we configure the relay. It has to be obviously a dual throw type relay, so that when it opens, even if an arc is struck, it'll just arc across from the relay contact, which is obviously connected to 0V, and it won't harm the speaker. Now if we look at the input, obviously there's our capacitor resistor filter circuit. I think it's probably about maybe 10 Hertz, something like that. This would kick in. Anything below that, the circuit would activate. So let's say the output of the amplifier had gone positive. This diode would be forward biased. The base emitter junction on this transistor would be forward biased. This diode would be forward biased, so emitter current would flow, collector current would flow. The resistor here, once 0.6 volts has been reached across this resistor, this transistor is forward biased. This then robs any base current drive away from this transistor, turning this transistor off. This transistor is just being turned on by this relay down to this resistor down to 0V. That's where it's getting all its base current from, and there, so obviously it's driving a relay. So if this transistor turns on, this one turns off. The relay coil is no longer energized, the relay opens, and the speaker's disconnected from the amplifier. This diode, obviously, there's other ways of doing this. This is about the most basic way you can do it. You could even do it with a resistor if you wanted. If you put just a diode across, it actually slows the relay down because it allows it to maintain quite a high current in the coil. Obviously, being a magnetic coil, when you remove voltage, the inductance of the coil tries to maintain the current flowing through it. If the current manages to keep flowing through it, the coil will stay energized, the relay stays energized. So it's just a simple diode resistor chain across here would actually make it open quicker, but this is just the most basic way. But obviously as the voltage pulse occurs on here, this diode will steal it, it protects this transistor. Otherwise, you could get such a high voltage pulse on here that it would actually exceed the maximum collector emitter voltage ratio limit on this transistor and break it, which you obviously don't want to do. Now if you look at this circuit carefully, you can see under positive fault conditions, the resistor here is only having to supply enough current to forward bias this transistor on and apply a small amount of base current. Under negative fault conditions, this diode becomes forward biased, the base emitter junction becomes forward biased, and the base current is actually supplied through 0V through this diode here. So this resistor here under a negative fault condition has to supply all the collector current, well, the emitter current, the base current, and the collector current for this transistor here. In practice, this doesn't particularly cause any problem because we only need 0.6 volts across this 100k resistor. So to supply enough current to do all that, we'd need about 0.6 volts across this 100k resistor. We actually have a greater voltage drop in either direction across the three forward bias semiconductor junctions. The three of them combined come to about 0.8 volts. So positive threshold would be about 0.8 to 0.9 volts. It would, 1.8 to 1.9 volts it would trigger. Under negative fault conditions, to actually get enough current for this transistor to be turned on, we'd need about minus 2.1 volts. 2.4, sorry, yeah. 0.6 times 4 is 2.4, yeah. So this is the very basic one. Now, as you can see here, obviously all the voltage from the amplifier has to appear across this capacitor. So if this was a very high voltage amp with say 100 volt rails, this capacitor would have to be able to withstand all that voltage. It also means that to configure it so maybe we wanted it to come in it just below our lowest frequency, so say we wanted it at 10 hertz, well, if we was only supplying a low voltage coming from the amplifier, say we was only driving a speaker quietly, this capacitor would see almost no voltage across it. It would just have a very low level ripple. Obviously, if we crank the amplifier right up so there's a big signal coming in, the amount of ripple on this capacitor would clearly be bigger. So you'd have to make sure with this circuit that the capacitor resistor combination doesn't false trigger the relay if you have a powerful amplifier which is being driven hard. And of course that can mean that you might have to find you slow the circuit down to a point where it may not operate as quick as you want under a fault condition. It also means if you have, say someone's plugging in, unplugging leads and it's just causing a low level transient, you might still want it to disconnect the speaker, but the attenuation by this network you've got, because you've obviously increased it for your higher voltage, it may not actually activate. So all in all, it's a very simple circuit. Under most conditions it's fine, but I was just being picky, so I thought, you know, how far can we push a circuit like this? So well, obviously come to that in a second. I should point out a few other things with this circuit. As you can see, as soon as I apply power to it, it's going to connect the output of the amplifier to the speaker. So let's say we turn the amplifier on, obviously everything comes on at the same time. If the amp, like a lot of amplifiers, might have a slight transient on it at first switch on, well, the circuit might connect the speaker, it gives it a loud thump through the speaker, or you know, a short DC pulse, which might not be quick enough to activate the circuit. It might be quick enough to activate the circuit, but either way, it's still going to be there, and then circuit doesn't activate before the amplifier settles down. So we want a small delay so that no matter what happens this end, it's only once the amp's had a chance to settle that we actually close the relay. Now, this basic circuit doesn't do that. Now, I know Rod Elliott, his circuit is a bit more complicated than this. There are a few other features to it, but this is just, again, this might not be his circuit. I know it's similar. I've seen it on his webpage before. It's something along these lines. But so we're going to put in, obviously, a turn-on delay. But I also want to put in, should, say, power be momentarily lost to the amplifier, I want it to disconnect the output relay again. Because, again, when your power amplifier's off, they can become unstable. If there's a momentary power lapse, say you've got a loose plug or something, say it's at it's a public address type amplifier, you're at a gig, you're at a village hall, whatever, and there's a dodgy power outlet, or someone, kick your lead and the plug's just making contact, and so obviously the power's a bit flaky. We don't want all those transients to keep appearing, as a fault condition on the amplifier, connecting and disconnecting the speaker, or making loud thuds and bangs coming through the speaker all the time. So we can add a circuit that detects that as well. So we'll look at my circuit in a second. Well, if you're still with me, thanks for watching. I do apologise if I went on a bit in that last section. I've just, I was getting a bit of a lump in my throat, and it's not till I stopped recording I realised that went on for about 10 minutes. So if you are still listening to me drone on, thank you very much. So here it is, my detector circuit. As you can see, obviously it's a little bit more to it than the previous one. Now, this is actually just a detector. I've got to show you the output circuit a bit later on. Now, this might look daunting or it might look complicated, but it actually isn't. All these is what's called an operational amplifier, and you can see there's just 5 of them here. You could pretty much use any generic operational amplifier, be it LM741s, any 5532s, TL072s. Basically, as long as it's a voltage differential type input amplifier, you can use them. Now, if you don't know what an op amp is, obviously what operational amplifier is shortened down to, your basic op amp, we just draw it as a block. You have, if you ignore the power rails, you have 3 basic connections. You have what's called the non-inverting input, the inverting input, and the output. Now, it's a differential amplifier, and that literally means it amplifies the differential between these 2 terminals. So let's say it had a differential gain of 1000. If we put 1 millivolt here and had 0 here, then on the output we would have 1 volt. It really is that simple. Now, you can literally write books on various ways to use operational amplifiers. You have feedback, you can have negative or positive feedback depending on how you run them, if they're a linear circuit, if they're a comparator. But there's a basic simple rule that they follow. The output will always try and match the most positive input. So if the input on the non-inverting side goes positive, the output goes positive. If the input on the inverting side goes positive, because it inverts, the output goes negative. So basically anything on the non-inverting side gets copied and amplified. Anything on the inverting side gets copied, inverted, then amplified. So it's, they're very handy little devices. You can use them in all manner of ways. In this circuit, I'm using them as comparators. Now, when you use a comparator, you can apply something called hysteresis. I'm not applying that in this circuit. It's not needed. So if we come along here, the first section we've got here is a loss of AC detector. So my AC signal, I'll just draw it in here. So let's say I'm feeding the whole circuit from a 12 volt AC transformer. Now I need a symmetrical plus and minus 12 volt supply. So let's say I've got a transformer with 2 12 volt windings on it. I'm rectifying them, I'm regulating them, and I've got my 12 volts for my positive supply and my negative 12 volts for my negative supply. But on that transformer, I can also take, where I've got my center tap, I can take one of the windings, it doesn't matter which one, they both swing positive and negative 12 volts. Well, 18 volts actually, but it's 12 volts RMS. So it would come through the resistor. This diode will only allow it to conduct when it becomes positive. It will charge this capacitor, and the voltage on this terminal will rise. Now, these 2 resistors here set a voltage reference which is constant on the inverting input. So if the voltage on the non-inverting input becomes more positive than this, the output of the op amp goes positive. If the input on the non-inverting input is more negative than this, the output becomes negative. Now, under normal circumstances, the output from this operational amplifier needs to be positive. So as long as their AC on here, obviously it would look as a waveform. You'd see it quite sharply rise, and then it would slowly fall down, and it rise, it would slowly fall down. It would keep doing this. So it depends, as long as it's not going, let me think this right, it needs to remain more negative. No, it needs to remain more positive than what's applied to our inverting input here. So yeah, it basically, as long as it stays higher than this voltage here, the output here will always be positive. So let's say we drew in our voltage reference. If we was to look, our applied high ripple half-wave rectifier signal needs to remain above this reference, which under normal operation it will. However, if their AC is lost, so we turn the amplifier off or fuse blows, power drops out, someone pulls the plug out of the wall, whatever, this resistor will quickly discharge this capacitor. It's only 1 microfarad, so it doesn't hold a lot of charge. The voltage on this will drop down below the negative rail. As the negative rail is more positive, the inverting side is more positive, the output will become more negative, and this gets fed through to a part of our detection circuit. Now, the way the detection circuit's configured, this would then ultimately go down the chain and disconnect the relay. The detectors themselves, you can see again we just have voltage references via resistor networks, and that sets these detectors at about 200 millivolts or so. I think I decided 150 millivolts, whatever it was. Basically, it sets them at a very low threshold. So once the amplifier starts going, as soon as it goes above or below that sort of 150, 200 millivolt threshold, these op amps actually start going crazy. They're constantly going from one rail to the next, one rail to the next. They do it in turn. These two, one monitors the positive waveforms, one monitors the negative waveforms. Now, if you notice, unlike the previous circuit, I have my signal coming in. I don't have any capacitor filtering on here. Basically, all I have is 2 diodes. They're clamping the voltage coming in at 0.6 volts above or below the 0V rail, depending on the polarity of the input signal. And I've done this because I want to be able to detect very low DC offsets. I've had amplifiers have strange fault conditions before where they've had a leaky capacitor or something, and that's caused, just a couple of 100 millivolts of DC offset. Well, if it disconnects the amp, and if my amp's not turning on, I know I've got an issue and I need to look into it before something bad happens. I also don't like any DC offset on my speakers at all. It stands to reason they're not meant to have DC across them, so the less you have, the better. So this circuit will detect very low levels of DC on the output of the amplifier. If you look here, I have 2 filter sections. These are for each side. Now, both of these op amps sit with the outputs negative when there's no signal on the output. As the output signal starts to come in, these op amps above the threshold voltage swing positive. They start to charge this capacitor, and obviously that signal is fed into 2 comparator circuits, again just being fed from a voltage reference. And as long as the voltage on this capacitor stays below the threshold voltage on either of these comparator circuits, again these comparators won't trigger. The outputs on these are actually configured to stay positive. No, they stay negative. Have I changed the design? I remember, yeah, I was going to have them negative, but I've now got it as positive. Now, when the polarity changes, the op amp here swings negative. It starts to discharge this capacitor through the resistor. These diodes clamp it. Come on, focus. These diodes here clamp it so it can only ever become 0.6 volts more negative than the 0V rail. This means I don't end up with, if I didn't have these, obviously under non-fault condition this capacitor would be charged negative. Whereas the amplifier started going, the average voltage would slowly rise up and sit around there. As the amplifier stopped, it would then drop down again. And depending on when I got my DC fault, it would take different amounts of time to trigger the detector circuit, which I don't want. Beauty of this circuit is, even if the DC threshold is near the detection threshold, it won't matter to the circuit. If you had, say, more like the more basic circuit, if you had a DC fault that was near to the threshold voltage enough to turn the detector on, when you actually applied an AC signal, as the AC went up, because you was already so near that signal, you'd end up triggering the detector. Well, this won't do that. So you can see it looks complicated, but it's actually a very simple circuit. If you break it down, you've got just a loss of AC detector based around a differential op amp running as a comparator. 2 differential op amps just running as comparators. The filter circuit and another 2 differential op amps running as comparators. And the output from these, you can see again comes through 2 diodes, so I can only pull any load on this positive. If it goes negative, it won't do it. This resistor here goes to 0V. That's for the next circuit. based on the 555s. So well, look at them again, and I'll go through why I've decided to feed the output from this to 555 timers rather than just a simple transistor trigger. Right, so this is the final timing and output control circuit. Now, here's where the input from our detector comes in. So it's normally there's nothing here. We've just got a resistor going to the 0V on the detector, so that just means this transistor stays turned off. Because this diode would be reverse biased until the output goes off the detector goes positive, it won't do anything. So this circuit is just standalone on its own. Now the detector transistor here, not detector, sorry, the output relay drive transistor gets its base current through this resistor here. So if this transistor turns on, the voltage here drops, this transistor turns off, the relay goes open. Ignore that, that's just a random artifact of drawing it out on the computer. This is basically just symbolizes a relay coil. That's just basically, you know, gives you an idea of what relay looks like. Connects exactly the same as we explained earlier on the simple connector. Now 555 timers are handy little devices. They're just a little 8-pin package thing. You got obviously you have a ground connection, you have a power supply, VCC, reset. If reset is high, the 555 is active. If it goes low, it becomes puts it into standby. A control pin, we don't really have to worry about that in this application. This actually connects to an internal resistor network which divides the rail voltage into two different voltages, one at 2/3 rail voltage, one at 1/3. You can actually use this pin to modulate the voltage on that, and when you're using the 555 in different applications. If you're not using control, you just put a capacitor to ground to give it some immunity from any noise, stop it from interfering with the way your circuit operates. Now on a 555 timer, if trigger goes below 2/3 the rail voltage, it sets the thing in motion. Once it's in motion, if the threshold pin goes above 2/3 rail voltage, it resets the circuit and it puts it back into the original state. Now in the initial state, the output is low, the discharge transistor is turned on, and so you know nothing can be driven from the output. You can actually drive something from the output, beg your pardon, because it's not open collector. It is actually capable of both sinking and sourcing current. So in our application, because the way it's configured, when the output is low, it does nothing. It's just making sure this transistor's got a nice little bit of reverse, not reverse bias, but it's got a nice path to 0V to stop any leakage currents from false triggering it. Now, this one here is what's called initiation on supply. When the supply goes high, this capacitor holds the trigger pin low for a fraction of a second until the supply raises up, because obviously the supply isn't instant, it takes a fraction of a second to raise up. Well, as the 555 gets a point, its minimum gets above its minimum operating voltage, the trigger pin is still low, so the circuit gets set in motion. The output pin goes high, the discharge transistor turns off, and this capacitor starts slowly charging through this resistor. This is, I think it's about 2 seconds or so. Once it gets above 2/3 rail voltage, which in our instance would be 8 volts, the discharge transistor turns on, it discharges this cap. At the same time that happens, the output goes low, and the whole circuit then could be set in motion again by applying negative pulse to the trigger. You can see as a resistor here, this capacitor by that point will charge to the 12-volt rail, and this circuit basically will operate once when power is applied, and then it will forever just sit in standby with the output low. When the output of this goes high, it turns this transistor on, it turns this transistor off, and obviously it stops the relay from energizing. Now, this happens almost instantly. Before this transistor's even got a chance to turn on and this relay energize, the 555 circuit will have turned on as well. And so basically, you know, there might be the slightest of attempts to draw a little bit of current through the coil on the relay, but it's no way near quick enough for it to operate. It's within fractions of a millisecond. It really is. Basically, it's to stop the relay connecting the speaker to the amplifier until we've given it a few seconds for the amplifier to just stabilise, DC protection circuit to stabilise, and everything to settle down. Now, from the output, you can see if the detector circuit detects a fault, whether that be the loss of AC circuit sending its signal to tell it to go high, or there actually being a fault on the amplifier. That's better, bit of focus. It can directly drive this transistor and turn the relay off. I also have this transistor here. If the output from the detector circuit goes high, you can see these two circuits are identical apart from this capacitor. This circuit won't be triggered on supply because the trigger pin is always at the same voltage as supply. It needs to be 2/3 the supply voltage for the circuit to trigger. So this circuit is just sat in standby waiting for a pulse on here. Now, should my detector even detect a fraction of a pulse, so again, if that's someone unplugging a lead or something, you know, the AC detector just flicking in for a fraction of a second, it will trigger this circuit in motion, and then this has again the same timing as this one. It will keep high for a couple of seconds on the output. It will obviously, the relay will be disconnected. It will wait for a few seconds for everything to settle down, and then it will reconnect the relay. Now, I could have actually just fed the output from this transistor to this pin here. It will have worked. It should have worked. However, you know, sometimes things don't always behave as you want them to. So, you know, if I held this pin low as the power supply ramped up, it might have upset the 555. It might just want to have seen a slight rise of voltage on here. It shouldn't have, but it depends on who's made it, how it's configured. It's also, you know, it's just a redundancy feature. These things are so cheap. And it separates the two circuits. And I've got a dedicated circuit for the timing initial switch on, and I've got a dedicated circuit for, you know, our detector circuit output to input. This means that this circuit's always ready to go. If something random, if we completely turn the amplifier off, this circuit or this capacitor is always going to be discharged. So upon initial supply of power, even if this rail's completely collapsed to zero, this thing's going to turn on the way it's going to go. Now, the same should happen here, because obviously as supply voltage drops, this capacitor voltage will eventually be the supply voltage if this was halfway through a cycle. Then the discharge should turn on, discharged it, and it should be ready to go anyway. But just in case, you know, I have two. One's dedicated to the timing it switch on, one is dedicated to the detector circuit. And like this diode here, I mean, technically I could have missed this out. I could have just used this transistor to trigger the detector circuit directly and use this 555. But, you know, you figure for the price of a 10k resistor and a small diode, you might as well put it in. Even if this circuit, if something goes wrong with this chip, it can still turn this transistor on direct from our DC detector circuit and disconnect the relay. These 10k resistors, you think there's 3 of them here. Now, obviously, whichever one of these goes high needs to win. There's no need to put diodes in here because obviously I only need to develop about 0.6 to 0.7 volts across this base emitter junction here to turn this transistor on. So whichever one of these goes on, it's always 12 volt, 12 volt, or 12 volt minus 0.6 from our detector circuit. So we've got basically sort of 11 volts to waste across each resistor, because above 0.7 this turns on. So there's no need for diodes here. It doesn't matter, you know, a small amount of current will be synced into the 555s. It's irrelevant. It won't affect the operation of the circuit. So yeah, I like this circuit. It's a very good way, I think, of putting a turn-on delay and a transient delay into the DC detector. It keeps it out of detector rather than trying to do it all with resistors and capacitors in the detector circuit. I've split my detector up into several separate parts, and obviously this being the final part, it just makes the circuit very reliable, very predictable, and it makes it very repeatable. So yeah, here's a basic 555 circuit. It is just this simple circuit here. So it will initiate on supply, and a negative pulse to the trigger will set the circuit in motion again. So if we look here, at present I have the supply supplied, man, that's bad English. I have the supply connected. Now this goes to our trigger pin, so if we just give this a quick flick, you have to bear with me, this is a bit tricky with one hand. Right. So you can see the wire is disconnected, the light is on, and off it goes. So we do that again, a quick. So now if I keep the wire in, you can see we've gone past our time period now, and the output is staying high. As soon as I disconnect the wire now, it goes out. Whereas normally, as you can see, I've disconnected the wire, it goes through its timing routine. So as you can see, so let's say this is, imagine this is a quick DC transient, bump, disconnects the relay, gives us a small amount of time, doesn't connect it. If our output sticks to DC, it will just stay activated, our relay will never come back in again until the DC fault clears. Now if we go, just disconnect the supply, you see as I reconnect it, you can see again, a small amount of time passes before it connects. Now I know I said earlier that I've used two circuits because I don't want to be trying to use the same circuit for the timing at startup and the timing for DC fault. Now if we actually test this, look, I've disconnected the power now. When I connect it, it is actually triggering, and it's going through the same routine. Obviously it's the reason the LED is not going out is because that's in there. However, for the price of a 555 timer compared to the price of a loudspeaker and the few components and the tiny amount of space it's actually going to take up on a circuit board, putting two in there is just a peace of mind. It's like a belt and breeches kind of thing, you know. It's belt and breeches, belt and braces. Man, my English is frigging terrible tonight. So yeah, that is the basic 555 circuit. So again, yeah, look, power supply off. So let's say we just had the one circuit. This is now under a DC fault. The amplifier, as soon as we turn on, the amplifier's done a DC fault. Well, it's still triggered. It's still timing up. I'll just pull my power supply out. Obviously, what I can't simulate with this, because I just can't move my hands fast enough, I can't simulate what would happen if it turned on and then momentarily after it turned on there was a DC fault. But it should just behave exactly the same, because all it's bothered about is once it's set in motion, it's looking for the voltage across these timing caps to go high. And as long as the voltage on the output is high, it will turn off. If the voltage on the, not output, if the voltage on the trigger pin is high, it will turn off. If the voltage is low, it will stay on. So yeah, this circuit, very basic circuit. If you're using the initiate on supply set like I have, you just need to make sure that your timing for your trigger is considerably quicker than your timing for your threshold. As you can see here, 22 microfarads versus 100 nanofarads. So there's a significant time difference here. So yeah, anyway, thanks for watching, and I've been waffling on, but so I'm gonna, like I say, I'm gonna be building this soon. It's gonna be hopefully in up and coming videos, and maybe I won't be waffling on so much, but it'll be more actually showing you stuff I've built rather than just the theory and the ideas behind the circuits. But yeah, anyway, thanks for watching. This is Liam 1981, and hopefully come back at you soon with something equally interesting or boring and just as waffly.